We have two parts in this problem. Part A, we sketch the graph of a function defined on the closed interval from -1 to 2 that has an absolute maximum but no absolute minimum. In part B, we sketch a graph of a function on the same defined on the same interval that is discontinuous but has both an absolute maximum and an absolute minimum. So let's start with part A. Then we want a function that has an absolute maximum but no absolute minimum on a closed interval. For the function got to be discontinuous because we know by the string value theorem that if the function is continuous and the interval is closed, it attains both an absolute maximum value and an absolute minimum value. So the function got to be discontinuous to have this result. And we have a sketch here, this graph. The function is defined on the whole interval from -1 to 2. That is, all points there has an image. As we see that we have a discontinuity at this value here. Sorry. I meant that at this value we have a discontinuity because the image is over here up, and this open circle means the image is not there but here up. And for that reason, this function has no absolute minimum because the lowest point should be this open circle here, but it's never attained, so there is no absolute minimum. But the function has an absolute maximum, in fact, on the endpoint, the left endpoint, -1. And then the only way to achieve that on a closed interval is that the function is discontinuous. So we have here absolute maximum, no absolute minimum. F has to be discontinuous because the interval where it is defined is closed. And if the function were continuous and the interval closed, the string value theorem implies that the function attains its string values and the solution will be impossible. But in this case, nothing said about the continuity as a function. We conclude that it has to be discontinuous, and so we draw a discontinuous graph having these properties of attaining an absolute maximum, in this case at -1, and no absolute minimum because the lowest point of the graph is not included in the graph. Okay, so we have part A, and now in part B we have used exactly the same graph, but we have changed the image of this point here. In part A, the image of this number here was here up, but now is here down. We move the image only, and only doing that, we have a graph of a function defined on -1, 2 that has both an absolute maximum here and an absolute minimum here, and is discontinuous at this point here, at this value. This means that the extreme value theorem is not an equivalence. That is, if the function is defined and is continuous in a closed interval, then it attains its extreme values. But if the function attains its extreme value, it doesn't mean automatically that it is continuous. And this is an example. So it's not an equivalence. It's an implication of only one direction. And we can say then that this graph has a function defined on -1, 2 that is discontinuous and has both absolute maximum and absolute minimum. And that's one solution to the problem given here.